So, good afternoon, everybody. The reason there are so many of us here today is because some of the audience are from the Sea Ice Prediction Network workshop, which is happening this 2 or 3 days this week. So welcome to you all. And the rest of the audience is the CGD Seminar Series audience, which we normally have Tuesdays at this time. So happily, Ed's volunteered to give this hour-long talk to fill that space. So today's speaker is Ed Hawkins. He he's at the University of Reading at the National Centre for Atmospheric Science there, and he graduated from Oxford in physics, first place, and then he got his PhD in astrophysics from Nottingham, and then evidently moved away from the dark side, moved back to Reading in 2006. He was a postdoc at Reading in 2006, and now he's a NERC Advanced Research Fellow, which is what all the cool people do in Britain. Anyway, and well, it's true, isn't it? Anyway, so he's going to give us a seminar, which I've been informed isn't only part of it is an April Fool's issue. So over to you.
Thank you, Rosie. It's great to be here. My first trip to Boulder. It's a beautiful place. So just before I start, in lieu of an April Fool's joke, I couldn't come up with an April Fool's joke. So it happens to be a big anniversary today for this chap and this paper from 1938. How many people know who this is? Okay, so three from Reading. I'm bored with this already, and I'm one at the back. We'll come back to this in a moment. So I'm going to talk a little bit about climate variability for the first half, and then as it's the Arctic Sea Ice Prediction Network meeting, I'm going to talk a little bit about Arctic predictability after that as well. So many thanks to a cast of thousands, all listed here, who are all involved in various aspects of this, particularly the Arctic predictability work as a long list. So just to get us started then, I'll start with a little bit of the history of climate variability, actually. So here we have, some of you may know this American chap, Joseph Kintzer, who in 1933 published a paper in the Monthly Weather Review titled, "Is Our Climate Changing? A Study of Long-Term Temperature Trends?" And he collected various time series from certain stations around the world. So we've got Paris, Vienna, Greenwich, Trinidad, Bombay, and Batavia. And there are lots of others in this paper. You can go and download and have a look at them all. So first of all, you notice several things. There's trends in most of these, warming trends. Some of that is probably the urban heat island effect. There may well be an anthropogenic component or solar component or many other aspects as well. There's lots of variability on top of these trends. Particularly, you can see in Trinidad there's warming, and then there's variability, perhaps cooling. There's variability, ups and downs, wiggles on top of any trend. And the other thing to note is that you'd see different amplitudes of variability. So in the sort of more tropical regions, you see much smoother trends, and in the extratropics, you see more ups and downs, more variability. I'm going to come back to that again as we go through the talk. You see more variability in the extratropical regions. So the fact that people knew at the time that the climate was warming up, they had all these long-term records. And so now we come to the answer to the quiz question. And this man is a chap called Guy Stewart Callender, who is an English engineer, an amateur meteorologist, who in 1938 published the first estimate of global temperatures, or saw first estimate of global temperature rise. So here's his data he put together. He got data from 147 stations around the world and published this time series showing a warming trend in global temperatures. And he also went quite a long step further, and he also had a very simple model for how much warming he might have expected from the observed increase in carbon dioxide. So they also knew that carbon dioxide was increasing from fossil fuel burning, and he came up with an estimate of how much warming he might have expected to see because of that observed increase in carbon dioxide. And so this is kind of the first detection and attribution, if you like, of global temperature trends to an anthropogenic influence. And perhaps you might say that the observed trend is actually larger than just the carbon dioxide trend. There's probably some variability going on here. There may well be solar influence and other aspects as well. But this is the first time that we saw an attribution of temperatures to carbon dioxide. So 76 years today, this paper was published. So we've known about the role of carbon dioxide for a long time. So how good were his temperature estimates? So here's the raw data. He tabulated the data so we can compare it. So here's the data that he put in his 1938 paper. He updated this about 25 years later for a longer time series, and that's the longer time series. So again, you see this warming, a bit of flattening perhaps at the end. So we can then ask the question, how well do these estimates match our estimates from today? So I'm going to add on the latest data from the CrewTem data set. And I think you'll agree he did a remarkable job of estimating global temperature trends back in 1938. And we published this anniversary note last year on the 75th anniversary. So today is the 76th anniversary. Okay, so sort of jumping to the side a bit, really. So as we saw in this diagram, we saw the last decade or so, we haven't had much warming. And of course, this has provoked a lot of interest amongst the public discussion and also scientific discussion about the causes for this hiatus or pause or slowdown or however you want to describe it. And I'm just going to make a little point here about how we interpret our climate model ensembles and how this interacts with what's been going on in this recent period. So here we see global surface air temperature for the recent period. We see quite a small trend over the last 15 years or so. I just want to make a point that when you often see climate projections from climate models for the future, you'll often see a rather smooth trend like this out in the future. And this is just an example using data from one particular model. You'll see just a smooth, gradually warming trend out into the future. But of course, what you don't see when this type of projection is presented usually is the fact that these are the lines that make up that spread. So there's lots of variability in our models, just like there is in the observations. And you'll see long periods, actually, in these other simulations where the simulations are outside the spread derived from the model. So we expect to see temperatures outside any smooth trends some of the time. I think that's an important point to make. But also, I think we're all too used to presenting things. This is kind of more communication aspect, really, of presenting smooth trends out in the future. We don't expect a smooth trend. We expect reality to look like a particular ensemble member, perhaps, with variability, got ups and downs with different amplitude trends. So this particular, one of the simulations, for example, has a very steep warming trend over the recent period, but out into the future, you see it's the coolest ensemble and actually has a complete flattening period out in the 2030s and 2040s. Short-term trends are not necessarily a guide to future long-term trends. And this is also, we're in Arctic meeting, so there are similar issues for Arctic sea ice projections. You know, the recent period, we've seen that the Arctic sea ice has declined faster than most of the models have suggested. So we mustn't necessarily straight away interpret that as being a forced trend. We may well have a variability component to it as well, and we need to be aware of that. Maybe we'll come back to that a little bit later. Just as another illustration of the role of climate variability in what will happen in the future. So this is, in the red line, we see the global temperatures that we've seen already. And on top of that is the black line, which is the temperature for central England. We've got a very long record of central England temperatures. So although we're used to seeing variability in global temperatures, actually, on small scales, we see very, very large variability, which disguises any long-term trend. You can see the trend in central England temperature. It's a very small region. England's a very small country. But you can still see a long-term warming trend. But so how does, say, temperatures in central England look for the future? And those of you at NCAR will recognize this type of diagram, Clara Dessa's work, as sort of trying to visualize what will happen out in the future. So if we take one particular model for what central England temperatures will do for the future, and I've highlighted two individual simulations here in the same way as I did before. So this is the same model. The only difference is the initial conditions. And what we see is that one model has a very, very strong cooling for a decade or so, but ends up in the same place as the red simulation. So variability, and this is only the same model, same forcings. The only difference is in the weather that the particular simulation experiences. So variability can have a very, very large effect on what happens over the next 10, 20, 30, or 40 years or so. And we must be very well aware of that short-term trends, again, are not a guide to long-term trends, especially on regional scales. So looking out into the future a bit more widely now. So here we have the projections from all of the models that have all 4 emission scenarios for the future. So these are 24 models run from, well, we've got 1950 to 2100 out into the future. So the different colors represent the different emission scenarios for the future. The pink one is the very high emission scenario, and the blue one, the low emission scenario, and 2 in between. So the thick lines are the ensemble means, and the thin lines are the individual models. And so you can see that there's different sources of uncertainty at different lead times. In this near-term period, you see that the scenarios are on top of each other, but out towards the end of the century, they're very divergent. But is this the right way to present this type of information for what's going to happen out in the future? So this kind of picks this arbitrary time horizon, really, 2100, to focus what's going to happen in some distant time into the future, which is a bit arbitrary. It's just a round number. It hasn't got any particular meaning. So instead, what you can do is flip the axes. So we're just going to turn the axes the other way around. So now we have time going up this way and temperature going this way. And what a lot of people do, they'll turn their head on the side to try and interpret this. But the point is, you're not supposed to do that. You're supposed to read it in this particular orientation. So now we have temperature going along here, and we have a magic number that policymakers care about. They seem to care about 2 degrees above pre-industrial for global mean temperature. And now we can look at uncertainty in what's going to happen in the future. Instead of uncertainty in temperature, we have uncertainty in time. So we can say that, for example, we're going to cross this 2 degree threshold in 2040 plus or minus a few years under the high emission scenarios. And that brings the communication of this much closer to home. It's much more relevant to people. Most people, many people alive today will experience this, will experience 2 degrees under a high emission scenario. And it just is a different way of communicating uncertainty in climate projections. That seems to be more relevant potentially for policymakers. So coming back to this way of presenting it, we talked a little bit about uncertainty. So as I said before, the thick lines represent the multi-model means for each of these emission scenarios, and the individual lines are the models. And so there's uncertainty from the fact that the different models give different answers. You can see there's a range of the pink lines and a range of the orange lines, and then there's a range between the different scenarios. And then there's this variability on top of each of the simulations. So there's 3 sources of uncertainty. We've got emissions uncertainty, we've got model uncertainty, and we've got the climate variability. And so we can try and break that down and try and look at the relative contributions of each of those sources of uncertainty. And so now what we see, instead of seeing those lines, we're now just seeing a shaded plume representing the uncertainty in the future projections. We've coloured in the plume corresponding to how important that particular source of uncertainty is. So in the orange area, we have the uncertainty due to the variability, those little ups and downs on top of the long-term trends. The blue area represents the uncertainty due to different models, and the green uncertainty represents the uncertainty due to different emission scenarios. And so you can notice several things straight away. The green area is far larger out at the end of the century, and so you're seeing scenario uncertainty is the largest, the dominant source of uncertainty at the end of the century. In this near-term period, what you see is that the uncertainty is dominated by the other 2 sources, the internal variability of the climate system and the model uncertainty. And so it's just trying to get a handle again on what is the dominant source of uncertainty. It depends on your lead time that you're thinking about. And so variability is very, very important for what's going to happen over the next 10 or 20 years. So you can think about different ways of representing this. Instead of looking at it this way, you can normalize it instead. And so you can say, now this is the fraction of the total variance represented by these different sources of uncertainty labeled here. So you see that in the near term, you see that variability is dominant. Model uncertainty is always very, very large, and scenario uncertainty grows out into the future. So that's for global temperatures. But how does this change if you look at, say, something a bit closer to home? So this is European winter precipitation, something which we've experienced a lot of in the UK this winter. We've had massive floods, so we care a lot about winter precipitation. And now what we see is that variability completely dominates for a very, very long period into the future. And that model uncertainty is still very important, but you can hardly see the green area, which is the uncertainty due to different scenarios. So the fact is, if you're worried about European winter precipitation, and actually precipitation over most of the planet, which scenario you use doesn't actually matter because the other two sources of uncertainty swamp the uncertainty due to different scenarios. And this variability is very, very important for lengthy periods. But how good are our estimates of variability? We've seen before that there's these plumes and all the models have got variability, but it turns out that the amplitudes of that variability varies a lot across the models. So here we have a global mean temperature from what's called the pre-industrial control runs. So these are 40 models, I think, showing global mean temperature. And there's no changes in forcing here. The models are just left to generate their own internal variability in global temperatures, so own ENSO and so on, and the rest of the variability in the climate system. And you can see enormous diversity in the variability characteristics from the models. You see, for example, the GISS models have very, very small amplitude variability. You see the INMCM model, very low variability. You see the Chinese model have lots of decadal variability. You've got the GFDL model, lots of decadal variability, and you've got the FIRE model, which is essentially almost white noise. And you see the different amplitudes of variability, as well as different sort of memory characteristics. There's very different variability on annual timescales and also on decadal timescales as well. So if we're thinking about the recent period, the recent hiatus in global temperatures, the amplitude of variability matters quite a lot for interpreting that type of event. If variability in the real world is more like the Chinese model, for example, then we might expect quite frequent hiatuses in global mean temperature. But if we're a bit like the GISS model, we wouldn't expect to see them very often because the variability just won't be able to mask out the long-term warming trends. So this matters quite a lot, and our models just do not agree on the amplitude of natural variability. And that's also true if we look spatially, so that's just the global mean. If we look at the spatial distribution of variability, so this is the interannual standard deviation of temperature at each grid point, and this is kind of an average model, if you like, and we see large variability in the extratropics, very low variability in the tropical regions, and that's consistent among all the models. But what isn't consistent is the amplitude of that pattern. We see lots of variability around the sea ice edge, both in the south and in the north. But a low variability model has, again, low variability in the same regions, but the high variability models have very high amplitudes of variability in those same regions. And so, again, this matters for interpreting trends that we see in the observations. If we live in a world where variability is very low, then, again, what we're seeing is more likely to be the force trends, whereas if we live in a world where the variability is very large, then we need to be very aware that variability is large and not to misinterpret the observations that we're seeing. So we have uncertainty in the actual amplitude of variability as well as in the amplitude of the signal we see. So we're used to seeing uncertainty in the magnitude of the response to greenhouse gases. So this is, say, for example, the same pattern, except this is now the signal of change out in the middle of the 21st century, for example. And we're used to seeing uncertainty in the magnitude of the signal. So this is a model which warms a lot, and this is a model which doesn't warm quite as much. There's a very similar pattern. You see more warming over the land than over the ocean. You see more warming in the Arctic than outside the Arctic. But the amplitudes are very different, and we're used to seeing that, but we're not used to necessarily thinking about the different amplitudes of variability as well. And so this leads to then thinking about, well, how big is this signal relative to the noise? So this is the signal-to-noise ratio. So if you were to divide one by the other, that would give you the signal-to-noise ratio. So how big is the signal relative to the local variability? And then you can start asking questions about when does that become bigger than some threshold? So for example, you might think about when does that ratio exceed 1? So when does the signal equal the amplitude of variability? And this is just an example which is in the IPCC report for the April to September season. And this is now, again, looking at uncertainty in time, the temporal dimension. we're now seeing the colors representing time. So we're looking at when the signal will emerge from the background noise of climate variability. And what you see is quite a different picture from what we saw just now with the amplitude of the signal. What we saw in the signal was there was more warming in the extropics and less warming in the tropical regions. But we also see less variability in the tropical regions. And so what we see is actually the signal of climate change emerge earliest in the tropical regions, even though the warming is lower, has lower amplitudes of variability, so the signal emerges much earlier. And so if we're thinking about impacts of climate change, for example, then for some impacts anyway, it's probably more likely that you will see those impacts when the signal becomes bigger than the variability that the particular ecosystem or human society is adapted to. You know, in the UK and in the US, we're adapted to the levels of variability that we used to experience. And so even a big change, which is small relative to that variability, may not be felt as much. But in the tropics, even a small change in temperature will exceed the variability that is being used to being experienced in the past, and so will seem like a bigger change. So yeah, we see the signal of climate change emerge earliest in the tropics. So that's true for the April-September season I just showed, and it's also true for October to March. The patterns are quite similar, except, say, over the northern extropics, you see much later emergence in the winter season than in the summer, where we just have more variability in the winter season in the extropics, and so it takes longer for the signal of climate change to emerge than it does in the summer, for example. And there's large uncertainty even in this quantity. So if we look at, for example, the number of models which emerge in any particular 5-year period, you see a large uncertainty in when this will happen. And that uncertainty is due to both the uncertainty in the signal of the change, but also uncertainty in the amplitude of background variability. And again, we need to consider the amplitude of variability a lot more than perhaps we have done in the past, because it is a very uncertain quantity. Okay, so that's the kind of variability side of things talked about. We'll probably come back to it in a moment. But now, as Rosie said at the start, we've got a big sea ice prediction network meeting here, and lots of people here from that. So I've decided to talk a little bit about Arctic predictability as well. So what's going on in the Arctic? Well, I'm sure we're all used to seeing this picture many times. This is the Arctic sea ice extent in September over the satellite era. We saw obviously the very low years in 2007, 2012, and 2013 was back up closer to the long-term trend line. So I mean, there's several things you might think about. Well, is a linear trend a particularly good representation of what's gone on? You might suggest that perhaps the trend has accelerated in the recent period. There's lots of variability again. So you know, there is variability even in Arctic sea ice, and we must be aware of that. Some of it's caused by different weather events, in particular the summers, and so on. But we must also be careful about how we interpret the trends potentially, because as we've seen, there is large variability in the climate system, and we must be careful not to overinterpret any acceleration. So just to give another little example, I've got this figure from Brett O'Nuti at ETH in Zurich, and this is September Arctic sea ice extent in 2 simulations over the roughly the same period, the satellite period. And what you see is that in the top simulation, you see perhaps an acceleration in the Arctic sea ice towards 0 in September, and in this simulation, you see a much slower trend. So you might say, well, you know, what's going to happen in the future? You might say, well, this one's accelerating. It might well go to 0 earlier than the one on the bottom. I'm sure you've all guessed the fact that actually, if you then look out in the future, they both end up at 0 at the same time. Because, for example, what you see here is that actually the sea ice recovers in this model. So we must be aware that it's plausible, at least, that our models do suggest that you can get periods where there's no change in Arctic sea ice. Whether that's going to happen in the real world is another matter. But we must be aware that this is at least plausible, according to our model simulations, that we might well get, say, a flat period, for example. And we must maybe communicate that more widely, that this is possible or plausible. Because I think the communication of the recent temperature hiatus, we hadn't communicated this possibility well enough to the public and to policymakers. We knew that it was possible and probable that it would happen, but we didn't communicate that more widely. And that's got us into trouble, I think. Okay, so now on to the sea ice prediction network. So since 2008, the Arcus search project has collected predictions of September sea ice extent each year. And there's over 300 contributions over the last 6 years or so. There's a recent paper by Julien about summarizing all of the predictions that have been submitted. And there's a nice web page you can look at as well. This is an example of the predictions that were given for last summer's sea ice extent in July. So this is, I can't remember how many there are, but there's quite a few here, predicting the September sea ice extent from July last year. And the red line here represents what actually happened a couple of months later. And of course, what you see is that the different methods are given by the different bars, and the different colors represent different types of methods. So there's statistical methods, there's sort of more complex model approaches, and there's heuristic approaches as well. But they give a very diverse range of answers from 5.8 down to nearly 3. So there's quite a large range. There's only one model which predicted higher than the observed, and that's the GFDL model, up there. She's very pleased with this. So I think it's very useful that this type of information is collected ahead of time. I think we have to be brave enough to issue forecasts. We shouldn't just rely on trying to retrospectively predict what happened. We have to be open at predicting what we think will happen into the future. And these types of approaches, I think, are useful to learning about how our models behave and learn about how we might improve forecasts for the future. And I think the discussion that we're going on this meeting will be how we maybe formalize this a bit more. This has been quite an informal process up to now, and perhaps we can just formalize this slightly and to move it into the future to make sort of real-time forecasts for the Arctic. So a couple of examples of efforts that have been made to explore how much predictability we have in the Arctic climate systems. There's a recent paper, and I apologize because there's so many papers, I can't highlight all of them. So Michael's up here, and this is one example from his paper. So here we have the skill for predicting Arctic sea ice extent from a particular GCM in hindcast mode. And so the colors are the correlation, and this is the predicted month. So if, for example, we're only interested in September, we look at this column, and this is the lead time. So this is predicting September mean from September the 1st, August the 1st, July the 1st, and so on, going back in time. And so you can look at how much skill there is in predicting the Arctic sea ice extent, for example, in this way. So they've got forecasts started every month, going back over the satellite era to try and estimate how much skill there is in predicting the Arctic sea ice. But of course, a lot of this skill actually comes from the trend. We've seen this large trend in Arctic sea ice, which automatically gives you high correlations such as this. So if you take out the trend, as Michael did, then you end up with a much greener, yellower picture than the red picture we had here. And so we still see quite high correlations for predictions, half a month ahead, if you like. So September sea ice has still quite high correlation starting from the 1st of September. But there's some interesting features in this diagram. Obviously, a lot of the skill has disappeared. But you also see, for example, that February seems to be very well predicted even out to a year ahead. So the dots represent still significance. So even 11 months ahead, it seems there's some significant skill at predicting February sea ice extent, for example. So it seems like winter may well be more predictable than summer to some degree, at least a few months ahead of time. You also see interesting features such as this diagonal line. So for example, if you're interested in predicting September, the last black dot here is and that's from a forecast started from the 1st of June. So the forecast started from the 1st of June has significant skill out until October. But if you move 1 month further back, to the 1st of May, that skill disappears very, very quickly. So it seems like there's a possibility there's some kind of barrier in predictability. That if you start after the melt season started, and kind of the 1st of June, you seem to be able to have some information about what will happen a few months ahead of time. Whereas if you start from the 1st of May, you may not have that information. So the question is, are these features in these operational predictions of trying to predict the real world, are these features due to observational model inadequacies? Are these real, if you like? Or is this the limit of predictability? Is this the best we can do at predicting the wiggles on top of the trend for Arctic sea ice. And there's several examples here of papers which have looked at operational predictions of this type. And there's broad consistency in the levels, features such as this and levels of predictability. So to try and understand this, try and answer these questions, we set up an international intercomparison project, which was going to look at what we call perfect model predictions. So we're just going to explore the predictability in the model world without worrying about the complicated, messy observations. So we're going to use a climate model to predict itself. And this gives some kind of limit on how well that model might predict the real world, perhaps. So what we do, we take a model simulation in black, for example, and we choose particular points in that simulation and branch off a lot of predictions from different points by, for example, just introducing some noise into initial conditions, butterfly effect, if you like, to generate an ensemble which subsequently diverges, and you can assess how much skill you have in predicting the black line, which is the truth, if you like. So this type of approach has been done lots and lots of times for sort of individual models. So we decided to look at a multi-model approach. So this is the UK Apposite project. We've got several people here from Apposite, and we've taken 4 models so far. We've got another 2 that are going to submit their data fairly soon, I hope. So we've got a model from the UK, HadGem. We've got the EC Earth model, we've got the GFDL model, and the MPI model. So the other encouraging point is that these models are also used for those operational predictions. And so we're seeing these features, such as increased skill in the winter and this predictability barrier in the operational predictions. And some of these models also now have these perfect model predictions. So we can try and look at features, see if these features are present in this perfect model world as they are in the real world, and try and learn about how many of those features are actually inherent to the model, for example, or they're due to some kind of inadequacy in the observations or in the models. So we've taken these 4 models. We've run simulations of 3 years length. We've chosen 8 to 12 different points in the control run, depending on the model, with somewhere between 8 and 16 ensemble members. Most of them have been started on the 1st of July to try and learn about predicting September sea ice extent. We have got some started from the 1st of January and the 1st of May as well. And we've done this in present day climate state. And if anyone wants to use this data, it is available. We're happy to share it. You could use this for non-Arctic studies or Arctic studies or anything else if you like. So please contact us if you want to use it. So some questions that we might like to ask with this. So we're trying to explore how potentially predictable is the sea ice in these models, where there are no biases, the models are perfect. How much inherent predictability is there in these models? And some of these are used for the operational predictions, so we can try and go back and assess potentially how much extra benefit there may be from the operational systems to what we're currently seeing. We might like to think about what lead times we can think about useful forecasts for particular users. How important is sea ice thickness for forecasts? We can think about designing experiments to try and understand. This is quite a key question. We're starting to get sea ice thickness observations from satellite. Can we assimilate those into models, and how much benefit might that give us? And so we can answer similar questions with some perturbation experiments to this type of approach. And we might like to think also about some other more speculative ideas, like is predictability different from more extreme years? Do you see higher or lower predictability for different years? So just to sort of summarize some of the results. So here we have some results from Stefan Teacher's recent paper in GRL. So the top panel, we have the root mean square error in the sea ice extent for the 4 different models, started from the 1st of July. So we've got the 1st of July, so we've got first year, second year, third year. And you've got 4 different models in the 4 different colors, as indicated by the key here. And what you see is that even though the mean states in these models are quite different, some models have a lot of ice and some has much less ice, but yet the errors in the predictions actually agree quite well. And so you see this quite a rapid growth in root mean square error, which means that we're losing predictability over the first 2 or 3 months or so, and then it kind of flattens off during the the freeze-up season, and you see a growth in error again out in the subsequent summer. And that's root mean square error. And if you look at another measure of skill, anomaly correlation, you see slight differences between the models now. You see a rapid decline in skill out for the first year or so, and then a bit of flattening off. But even out at 3 years, there is some significant skill apparently in these systems out for about 3 years. Whether this is useful or not is another matter, but it does seem that there is some slow timescale variation that's captured by this type of approach. And the black line is the multi-model mean. So there does seem to be some inherent predictability in Arctic sea ice in the models, which it seems to be we can at least capture some of this in these operational predictions. Of course, we're not just interested in extent; we're interested in volume, for example, Pan-Arctic ice volume. And you see similar features. You see similar growth of error in volume out for the first year or so. And again, the correlations can be quite different between the models. But again, there's significant skill out for 3 years. So if we can initialize the models correctly and they're representing the real world adequately, it seems like there is some potential to make skillful Arctic predictions. So how does the spatial pattern of those errors change? Because although we're very interested in just the average quantity for September, for example, if we're interested in particular users, then we need to know about the spatial patterns of those errors. So these are the spatial patterns of error. So this is the ice concentration root mean square error, and spatial patterns in the 4 different models for the first September after 3 months lead time. And you see similar patterns amongst the models in that the largest errors are towards the ice edge, as you might expect. So you can see the different mean states slightly here. That you see the ice edge highlighted by the colours. But so there are large errors here. There's 20, 30, 40% concentration errors, even out at 3 months, even in a perfect system where you have perfect knowledge of everything. So we need to be aware that there are these inherent limits to predictability. If we look at the subsequent March, so after 9 months, again you can see that the patterns have shifted out to the ice edge. And so we can predict the middle of the ice because it's always frozen, but the errors are obviously around the edge and the variation in where the edge is in each particular March, for example. And then if we look out at the following September after 15 months, so a year or so later, you see that this pattern is the same. The amplitude has just grown enormously. So this highlights the fact there is predictability because the amplitudes of patterns are very different from September to September. So this is kind of almost saturated error. So and this is far less than that. So we seem to show some predictability, but it's by no means there are inherent limits to how skillfully we can make predictions with these models. And you can also learn about the processes responsible, and that's one of the key things we can learn from the models we can't do, say, from the operational predictions, is what causes the growth in the errors. So if we're thinking about the sea ice thickness, there's sort of, in the models anyway, it's split into 2 different processes. So there's changes in thickness due to the effective processes, and there's changes in thickness due to the thermodynamic processes. And the thermodynamics dominate the seasonal cycle, for example, but the growth in errors in thickness mainly comes from the effective processes, so it's the winds, essentially. So because we can't necessarily predict the synoptic conditions over the Arctic in a particular summer, is the effective of the winds, the fact that the winds are different in each of the different ensemble members causes the growth in thickness errors as essentially the ice is blown away or into the coastlines. So this tries to sort of understand what processes are causing the growth in the errors in the models, and that's potentially quite useful. And there's similar results for the other model where we can do this breakdown. So it seems to be consistent among at least 2 models that most of the errors come from the effective processes, not the thermodynamic processes. Now coming to the other question about the start date dependence. So in the operational prediction systems, we saw that there's a predictability barrier if you started in June or July compared to May. There seemed to be a barrier. If you started in May, you lost skill very quickly, whereas if you started later in the summer, you kept the skill. And so we've run some parallel predictions starting in January, May, and July with one particular model, the HADGEM model. And this is the root mean square error in the sea ice extent. And this is papered by Johnny Day, which is in press at the moment. So if we look at the black dots to start with, this is the root mean square error in the Pan-Arctic extent from the January start dates. And then the blue line and dots represent the root square error starting from the May's, and the red from July. And what you can notice is, for example, if you're trying to predict September, which is this peak here, if you start in May or January, there's very, very little difference in the root square error. Whereas if you start just 2 months later in July, you've reduced the error by a factor of 2. So it does seem like, for example, if you want to predict September, then starting in January or May, it doesn't really matter. But as soon as you start later in the summer, when the melt has started, you've gained quite a lot in potential predictive skill. That sort of tries to inform the design of these ensembles and sort of kind of getting again at the limits of where we might see this predictability. And then one other last little figure from a different group at Reading. So this is the CPOM group at Reading, David Schroeder and Danny Feltham and colleagues, some of you will know. And they've got a paper in press that's about to appear in Nature Climate Change. Again, trying to understand the processes responsible for providing predictability. And they've added a representation of melt ponds into the SICE model. And they've used that representation of melt ponds to try and make predictions of September sea ice extent from the spring pond fraction in May and June. So this line shows, for example, the black line shows the observations of September sea ice extent. The red line shows a set of hindcasts with their particular forecast of September sea ice extent using the data up the melt pond fraction up to June the 25th. So they built a statistical model of predicting the September sea ice extent from the melt pond fraction. And the blue line shows a forecast where they essentially have only used data up until the start time. The red line uses data from the entire time series, so it's effectively cheating because they're using data in the future when they're making predictions. But the blue line shows their true forecast, where they're only using the data up until the start time each time to make their forecast. And interestingly, their 2013 forecast, which was made before 2013, I had a chat with them before September, so I do know that it was made before the summer. It was actually for a high extent last summer, for example. So that's about to appear. And so the final question is then, why are we interested in all of this? So I have a PhD student, Nat Millier, who's looking at Arctic shipping. So that's one of the key users that might particularly find this information useful. And we've been looking at a particular case study. This is the ship, the Ob River, which was the first liquid natural gas tanker to cross the Arctic in November 2012. And you can see it ploughing through the Arctic here, accompanied by an icebreaker. And this is the route that ship took, starting here, North Norway, and making its transit across the Arctic. And the colours show the sea ice thickness as observed from satellite for the particular period it was travelling through the Arctic sea ice. So you see the route that it took across the north coast of Russia, and it entered the ice here, and actually took quite a sensible route, if you like, because the thickness colours, so the pinks and the blues show the thin ice, so it actually travelled through the thin ice rather than going close to the coast where there was thicker ice, or out in the middle where there was thicker ice. So it actually took quite a sensible route, according to the data from the satellites, for example. Except for this it took a bit of a kink here. We don't quite know why, but it seemed to go through some thicker ice if we trust the satellite observation. So we're trying to understand why particular routes are chosen and how we might think about whether we can predict useful information to try and inform these shipping routes so that there are less risks in the routes they choose. So to summarize then, talk a little bit about climate variability and uncertainty. Variability is the dominant uncertainty for near-term climate projections, especially on small regional scales, and we mustn't forget that. This concept of the emergence of the climate signal from the background noise seems to be very useful, especially if you think about impacts. Where do you see the impacts expected to see first, and when might you expect to see that? Looking at the uncertainty in time. There seems to be a large potential for useful Arctic sea ice predictions a season or so ahead, and we're beginning to see the development of operational systems to try and realise that potential skill. But there are significant challenges remain, especially with the models. They're still particularly poor in some of their processes and representations of sea ice and the seasonal cycle and so on. We still need to improve the models and the processes. And the melt pond example I showed that if you introduce new processes into the models, it can change their behaviour quite a lot. So we need to think about that a lot more. There's problems with initializing the simulations with the sea ice, especially the thickness, which we don't have particularly good observations of in the past. And we still need to understand Arctic variability a little bit more. How much of the recent trend is due to variability and how much is forced, I still think is a slightly open question. This perfect model approach I outlined is, I think, providing some useful information on the processes that are causing error growth in the models, useful information on the predictability, how we design ensembles, how we evaluate skill, and so on. Thank you very much.
I'm not going to comment on the irony of the natural gas tanker. Anyway, who has questions? 1, 2, 3, 4. Right.
So you showed a very interesting picture of the spatial variability in the CMIP5 models with the sort of 10%, median, and 90%.
Yep.
And what I didn't get was, what you showed, I guess it was the model noise, and then below that you had the signal. Now, are those from the same models, or that's from the spread? You're not.
So yeah, so that's a good point. So I didn't make that point very clearly. So this is done on a grid point by grid point basis.
Okay, so you're not implying, you're not implying that the models with higher interannual variability have higher signal.
They do tend to be the same models, but I've done it grid point independently in this particular example. But the patterns in the models are very similar. But yeah, so this pattern is not necessarily from one model alone. Yeah. So I've just looked at the grid point by grid point.
So in the places where you have more variability, you also have higher signal?
So yeah, so I guess, so for example, so are you asking whether there's a relationship between variability and sensitivity? There are small hints, but there's not a clear emergent constraint on for example, the signal from the noise, unfortunately. We might have hoped that there was some relationship, and there are small hints in some regions, but I wouldn't be very confident about how real that is.
Ed, I can't help myself but ask you about the hiatus. I mean, I agree with you that this recent event was plausible, but it also was found to be highly improbable. By some estimates, by one estimate, maybe a 1 in 500 year event given independent 20-year samples. So have we done so poorly by in our communication of the message?
I think part of the communication, we haven't done the communication very well at all. We do see hiatuses in the force simulations. We see lengthy periods of cooling in the control simulations. I wouldn't go as far as to say it's 1 in 500. I mean,
under current rate of forcing conditions, it is the case that that natural variability to overcome the forced warming is a very unlikely occurrence, even in the model.
Okay, so I've probably got an extra figure actually, which I didn't include. So, for example, I was going to show that, but I didn't have time. So here we have the global mean temperature. So I showed the 42 models. If you plot the model's global standard deviation against the redness, the AR1 coefficient, you just assume that they're an AR1 process, you get the crosses, and you see this enormous diversity. So you see the fire model down here, which has got essentially white noise, and you've got the model up there, which is very, very red with a high lag-on autocorrelation. But you see this enormous spread in the standard deviation. So if you were to assume that the forced trend is 0.16 Kelvin per decade, you can then model how likely a hiatus is given this AR process. And if you're out here, so these 5 models, it's more often than 1 in 5 decades. So one in 5 or more decades should show a hiatus. If these models are right, then it's less than 1 in 50 decades. So we need to understand where in the real world we are on this, because it makes a big difference to how we interpret the recent period. And of course, some of the recent period may well be forced as well. We've seen small volcanic eruptions and the decline in the solar activity. So it may not be that variability is doing all of it, but it may be doing some of it. And so again, that changes the picture again.
Yeah, I was very interested in your graph showing the prediction from melt-prone fraction. And I wonder if you could say a little bit more about is that some kind of a multiple regression model or something more elaborate?
So, yes, that wasn't my work, and I'll try and do my best to talk about it. So, what they've done, so David Schroeder and Danny Feltham and colleagues, they've taken the SICE model standalone, and they've forced it with atmospheric reanalyses, and they've incorporated melt ponds into the SICE model, and they've generated the fraction of melt ponds from SICE forced with the atmospheric reanalyses, and then they've built a statistical relationship between the spring melt pond fraction and the subsequent September ice extent, and then applied that in forecast mode to try and make the prediction. So I hope I've done that justice, but it's about to come out, so you've got to read all the details.
Yeah, thanks for the talk. Moving back to sea ice. Moving to sea ice, we are already in sea ice, sorry. General question. One key aspect for guiding the improvement of prediction could reside in the need to go to more complex models. Were you able to see trends in the predictability of your models as compared to their complexity? So, for example, do more complex models have longer predictability in volume, in area, and you only have 4 models, so it's probably not very robust, but if you can see some trends in this ensemble?
I'll maybe pass that question over to Stefan. Mm-hmm.
So it seems there's not really a simple picture. Certainly the mean state is not the decisive factor. What it boils down to, at least in my view at the moment, is that the more persistent models have more predictive skill. And whether the sea ice physics is more elaborate or not doesn't seem to be deciding.
So staying with the sea ice, and kind of the theme of how you evaluate predictions, and I thought your plots showing RMS error versus pattern correlation were quite interesting, because you get a totally different view when you're evaluating predictions if you're using RMS error versus pattern correlation. I assume that's because the trend comes out better in the pattern correlation, because you see this big seasonal cycle of the predictability, that one, in the RMS error and not in the pattern correlation. So I wonder if you could just comment a bit more on how you view this and which metric you pick to evaluate.
So I think it's always going to be important to use multiple metrics and not just these two. I think we also need to move to more probabilistic measures of skill rather than deterministic measures. And I think that's hopefully something that's going to come out a little bit more over the next couple of days. And also, what this type of metric for the pan-Arctic quantities does is disguise the regional patterns, for example. So if you look at regional patterns, you see particular regions where the errors are large. And you can often get anti-correlations between different regions, which means your errors in the pan-Arctic extent are smaller than you might infer from integrating the patterns. And so you have to be aware that you're not disguising kind of compensating errors in spatial patterns by looking at the pan-Arctic extent, which is obviously a kind of iconic measure, but it's not going to be so useful for people making decisions. What matters is where the errors are, and they're around the ice edge, according to these models anyway. So we certainly have to look spatially, we have to look at multiple metrics and think probabilistically, I think.
Any further question?
Thank you, Ed. You spoke about seasonal annual cycle to some extent in predictability, but can you speculate about a little bit more about the existence of interannual variability in predictability, or, for example, what would be the difference in predictability in the Arctic Ocean with less ice and more ice?
So we haven't looked at that question in particular yet. We do want to look at the state dependence of skill. Are more extreme years more predictable than average years, if you like. So we certainly want to do that with these simulations. Other groups have done work looking at predictability in kind of future, or also in a changing climate and also a future climate as well. So I'm probably not the best person to answer that particular question, but we do want to look at the state dependence of the predictability, but it will also change with time as we go forward into the future, without a doubt.
Take one more question.
I had a question about change in the nature of the variability with time. You showed that picture with the 40 different models and the variability that they generated. It's different from model to model, but within a model, it looks like it's pretty constant with time, either the range of frequencies and amplitudes generated by the model. And I'm wondering if any of the models can account for a change in that with time. And I'm asking because in certain places in Canadian waters, the Gulf of St. Lawrence in particular, based on 45 years of data, if you do your spectral analysis on the first 25 to 30 years, you have a distinct peak at 12 years, decadal variability, and if you use the last 20 years, it's just devolved into interannual noise. The peaks are all in the interannual range.
So that's a good question. I think a lot of these models seem to show a decrease in variability into the future. So and particularly in the high northern latitudes, as the sea ice retreats. So what you see in these diagrams is that variability is around the sea ice edge, the highest variability. And as the sea ice retreats, that variability follows the sea ice edge, so it moves further and further into the Arctic. And so actually, if you look at global temperature variability, it looks like it will decrease slightly, and the regions where you see high variability will move further along with the ice edge. So I think the variability will change with time as well. Yeah.
Okay. Thank you all for squeezing in together so well. Thank Ed again for his great talk.